السلام عليكم ورحمة الله وبركاته طالباتي وطلابي الأعزاء، أهلا بكم ومرحبا مرة أخرى. Welcome back to Physical Chemistry Lab 1 Chem 355. This course is presented under Chemistry Department, College of Science, United Arab Emirates University. And inshallah today experiment number 6, I think, which is entitled Binary Solid Liquid Phase Diagram. Our objectives for today, we need to construct the solid liquid temperature composition. Tx, T means temperature, X means composition, and it will be the mole fraction phase diagram of AB diagram of binary system of substance A and substance B. During this presentation, you will see some concepts like heterogeneous equilibria and homogeneous equilibria, Gibbs phase rule, reduced phase rule, eutectic point, and eutectic composition or eutectic mixture. And also you will see bi-mono invariant. What does it mean? Everything of all these concepts, it will be cleared in the next slides, inshallah. Okay, homogeneous equilibrium, from its name, we are talking about solution formation or forming solutions. So you need to mix more one component together and see what comes out. If you have, say one phase solution or different phases solutions, so it depends. So if you have one phase or a single phase, you end up with homogeneous solution or homogeneous equilibrium. So homogeneous equilibrium is an equilibrated system that contains products and reacts in a single phase. Products and reacts in a single phase, just you have one phase after mixing. Okay, you could imagine that product and reactants are solid and solvent to form a solution, and so on. In other case, or in the opposite side of homogeneous equilibrium, it will be heterogeneous equilibrium. And this one is a system whose reactants and products or both are in more than one phase. It could be 2 phases, 3 phases, etc. So this is heterogeneous equilibrium. Okay, we are going to construct a phase diagram of binary solid liquid phase diagram. So we need to talk about phase rule. What is the phase rule? Actually, the phase rule is a relationship among the number of chemical constituents, chemical components, and the number of phases of that constituents, and the number of intensive variables that must be specified in order to characterize an equilibrium system. So you have equilibrium system, and you need to describe it. You can describe this system by using the phase rule, which is a relationship between number of components, it will be C, and the number of phases, B, and intensive variables, it will be temperature and pressure. So we will replace these pressure and temperature by 2. Let's see. So the rule which studied the phase diagrams between different components, it's called the Gibbs phase rule, and it's given by the following equation: F equal C minus P plus T, where F is the number of degrees of freedom, عدد درجات الحرية. C is the number of components, عدد الكومبوننتس اللي موجودة عندك, 2 or 3 or 4 and so on. P is the number of phases of the system you have. If you have single phase, 2 phases, 3 phases, and so on. and 2 are the microscopic variables, which are temperature and pressure. So, okay, F, the term degrees of freedom represented by F in the phase rule equation is defined as the least number of variables factors, concentration, pressure, and temperature, which must be specified in order to describe the system, which must be specified so that the remaining variables are fixed automatically and the system is completely defined, completely described. Okay, that's good. Let us have an idea about phase diagrams and one component phase diagram and two component phase diagram, which we are going to reconstruct today, or which we will construct today for the binary system. For the one component system, this is very famous phase diagram. Actually, it's this phase diagram is for water, and it's you can know it from its shape. You can it's completely known, and you can know it's a phase diagram of water or something else because phase diagram has some features, especially the solid liquid line with a negative slope. The other substances, you will see this line with a positive slope, okay? And might be I will give you some hints about this slope and its applications and so on. So for one component system, it means you have one component, and in that case, it will be water. All these are water in different phases, okay? So F, C, it's 1, and P, it depends on the area you are talking about. You are the area under consideration. So if you substitute with C by 1, you end up with F equal 3 minus P. And in that case, P is the number of phases. Now we are going to talk about different areas. This one, for example, solid area, liquid area, and vapor area. And we are going to talk about any line of these phase diagram. And we end up discussion for this phase diagram by this point O, which is called eutectic point. Or triple point, sorry, triple point. Okay, let's see. In the first case, when only one phase is present, you have already C component equal 1, and we substitute by phase by 1. So 1 minus 1 plus 2, you end up with the number of degrees of freedom of Gibbs phase rule equals 2. And in that case, we call this system, it's a bivariant. Bivariant. Thus, the system is bivariant. I'm going to discuss in the next slide what's bivariant, what does bivariant mean. Okay, so you have one phase. The system is bivariant from the relationship of Gibbs phase rule, and it means it can be completely defined by specifying two variables. And in that case, it will be temperature and the pressure. So bivariant, it means you can describe the system with two variables, and in that case, it will be temperature and the pressure. Both the temperature and the pressure can be varied independently. What does it mean? Therefore, a single phase is represented by an area on PT graph. So if you are here, for example, or here, for example, or here, you have one phase. Could be liquid phase, solid phase, or vapor phase. So at any point here, you can move without any restrictions. If you move from up to down here, for example, say to say, or from left to right, you still one half phase. You keep considering just only one phase, so temperature and the pressure can be varied independently. Okay? Also here, you can go from here to here, and you still have solid. From here to here, from here to here, you still have vapor. So here, the temperature and the pressure can be varied independently. Okay, so you have a single phase in any area which I showed you. Okay, let us discuss case number 2, in which you have two phases in equilibrium with each other. It could be solid and liquid phases, or liquid and vapor phases, or solid and vapor phase. Okay, this curve, it's called fusion curve or freezing curve. It's okay also. Here it's a boiling curve or vaporization curve. It's the same. Here from solid to vapor you have sublimation curve. You have sublimation curve. Okay. Now we have two phases. Okay. This means that if you apply in the phase rule, Gibbs phase rule, it will be 3 minus 2. You end up with the number of degrees of freedom 1. And in that case, the system is monovariant. The system is monovariant. What does it mean? This means that the pressure cannot be changed independently. The pressure cannot be independent, cannot be changed, cannot be varied independently. Also the same, the temperature cannot be changed independently. I will show you. If we change the temperature, okay, so the pressure cannot be changed independently if you change the temperature, and the vice versa, it will be the same. Okay, temperature cannot be changed independently if you change the pressure. The pressure is fixed automatically if you change temperature, say to say, for a given temperature. So a two-phase system or two-phase system is depicted by a line in the PT graph. P means pressure, T temperature graph, pressure temperature graph. So any line here is represented or is representing two phases. So for example, if you at that point and you would like to go from that point from here to here, and you need to keep the two phases. If you go from here to here, okay, you change the pressure, say to say, the temperature will change it automatically. Okay, so you are not free to change temperature in this direction. If you move in this direction, say to say, so you will go away from the equilibrium between liquid and solid. So if you change pressure, the temperature will be changed automatically. Okay, so monovariant. You cannot change temperature and the pressure independently. See, also the same here. If you'd like to keep the equilibrium between liquid and vapor, if you change the temperature, the pressure will be varied automatically. Okay, so at any line on this diagram, there are equilibrium between two phases. Okay, and the system is monovariant. That's great. Okay, let us go to the case number 3, in which you have 3 phases. 3 phases, the number of phases are 3. If you apply in the Gibbs phase rule, 3 minus 3, you end up with 0, which means the system is non-variant. So you cannot change temperature and pressure, and you still have the same equilibrium. It's non-variant or invariant. So the system is non-variant or invariant. This special condition can be attained at a definite temperature and pressure. You cannot change any microscopic variables, and you still keep the equilibrium. So the system is therefore defined completely, and no further statement of external condition is necessary. Actually, this point or this monovariant system is represented by point O here, only point. It's called the triple point. And you can define the triple point, the point at which, or temperature at which you have 3 phases. All of them are in equilibrium, solid and liquid and vapor. And you cannot change the temperature or pressure at that point, and you still have the same equilibrium. So it's non-variant. Okay, it's called the triple point. Okay, that's great. The system is invariant. 3-phase system is depicted by the point on the PT graph. At that point, the 3 phases, solid, liquid, vapor, are in equilibrium with each other, and therefore it's referred as a triple point. And remember that you cannot change any microscopic, any variable. Temperature, you cannot change temperature, you cannot change pressure, and you still have that kind of equilibrium. Now we'll go to our system, or today's system. We are going to discuss two component system. So C, it will be 2. Okay, and we are going to discuss number of phases. If you have P, you have only one phase, homogeneous mixture, so to say. So just apply in the phase rule 2 minus 2 is the C, number of component, and 1 number of phases. And this is microscopic variables or parameter. You end up with 3 if you apply with these two values, which means, okay, this means that 3 variables must be specified in order to describe the condition of the phase. If you have number of degrees of freedom equals 3, means 3 variables have to be specified in order to describe the system. In addition to temperature and the pressure, you need a composition. You need a composition of one component. And the composition of first component will be known automatically. So in addition to the pressure and temperature, the concentration of one of the components has also to be given. Okay, solid liquid system with absence. Okay, now we are talking about solid and liquid. So there is no any contribution of the gaseous state. So solid liquid system, we call it condensed system. We call it condensed system. And what does it mean? It means that the absence of gaseous state or gas phase. So it's called condensed system because we are going to use or to study solid and liquid. In that case, you have no gaseous state. It means the pressure will be constant. So the pressure variable is considered the constant. So you can change that too with only one. So you keep pressure constant, say to say. And this leads us to reduce the phase rule. Okay, now you have C, two component system, C equal 2, and P1, you end up with 3. We agree together these 3 microscopic variables are temperature and the pressure and the concentration of one of the component. So the experimental measurements of temperature and concentration in condensed phase are also carried under atmospheric pressure, so the pressure is constant. So since the degrees of freedom in such a case is reduced by 1, we may write the Gibbs phase rule in another form, which is called the reduced phase rule. Okay, and we represent it by F dash C minus B plus 1 instead of 2. Okay, where F dash gives the remaining degrees of freedom you need to know in order to describe the system. Reduced phase rule is more convenient to apply for the solid, liquid, or for the condensed phase or condensed systems. Okay. Okay, now you have C2 and P1, and you have F at constant pressure, you have F dash equal 2. So you need to describe, in order to describe the system, 2 variables are needed. Okay, we have already fixed the temperature, so you are going to create a diagram between temperature and composition. So 2 variables of the 2 components solid liquid system, which are temperature and the composition. And the composition in that case, or here we use mole fraction. I'm going to show you how you calculate the mole fraction. We have already discussed before in the previous experiments. Okay, I'm going to discuss that with you. So the phase diagrams for such systems consist of temperature concentration or temperature composition graphs. T, C. T means temperature, C could be composition, it could be concentration. Both are the same. So composition and temperature. And the curve will be something like that one. Okay, actually our experiment for today, just to create a curve like that, we end up with a curve like that exactly, if you do an experiment in the right way. And let us, okay, discuss with you some on this graphs, temperature composition graph. Okay, you have 2 lines, say to say, and here you have pure A, and here you have pure B, and this it will be the boiling point of pure A, and this one it will be boiling point of pure B. And actually the boiling point of pure A decreases with increasing the composition of the other component B. The same is true with respect to B. This is pure boiling point of pure B, which decreases with increasing the percentage of A till you reach a point which is called the Eutectic point, at which the lowest boiling point of the mixture is obtained. أقل درجة غليان ممكنة لهذا المixture. Okay, above this curve, okay, you have one phase solution of A and B. It's one phase. Okay. Down this curve you have two phases. Okay, when you cool down, okay, pure A is separated, and you still have a solution of BA. Okay, at that on this you could say on this line. On the other side, here you have a solution, one phase. Once you cool it down, you end up with solid B plus solution A and B are in equilibrium with each other. Here you have equilibrium between that solution and solid B. Here you have equilibrium between solid A and solution of B and A. Okay, this point is called the eutectic point. It's lowest boiling point of the lowest boiling point temperature of a mixture between A and B. Okay. Okay, that's good. So it's called TC graphs or T concentration graph. Okay, simple eutectic system. This is our system for today's experiment. Our system will have eutectic point. Component A and B are completely miscible in the liquid state. This solution on cooling yields only pure A or pure B as a solid phase. Once you cool it, you end up with solid A here or solid B here. Okay? Let us talk about curve AC. AC, what does it mean? Okay, AC, it's a freezing point curve for A. Freezing point curve for A. Once you cool down, you separate A as a solid. This curve AC shows the freezing point of A, which decreases by increasing the value of the other component, which falls by addition of substance B to the substance A. Solid A is in equilibrium at that line. Solid A will be in equilibrium with liquid solution of B. Okay, is in equilibrium with liquid solutions الاثنين دول مع بعض, B and A solution. If you would like to apply phase rule at that line, you have two phases. So, okay, you have two components minus two phases plus one, you end up with one. So the system is monovariant. At that line, it's a monovariant. Also at that line, it's a monovariant. So the degree of freedom is one, i.e. the equilibrium is monovariant. So one variable can be changed, and the other one will be changed automatically. What does it mean? It means the composition and temperature cannot be varied independently. If you change the temperature from here to here, okay, the composition it will fix it automatically. Otherwise, you cannot move from here to here. You will skip the equilibrium between these two pure solid A and solution B with A. So it's a monovariant. Okay, the curve BC, it will be the same. This is the boiling point of pure B. The boiling point, this curve BC, the freezing point of curve B, of substance B. The point B shows the freezing point of pure B. The curve BC shows that the freezing point of B falls by addition of A and B. Of A to B, I'm sorry. Solid B is in equilibrium with liquid solution of two components. So here, it's equilibrium between B and the solution of A and B. If you apply phase rule, it will be the same. You end up with monovariant system. like AC line. That's good. Now let us talking about the point C, which is called the eutectic point. Here, the number of phases are 3. You have solid B and solid A and solution of A and B. And all these phases are in equilibrium with each other. So in that case, you have 3 phases. Okay, solid A and B are in equilibrium with the solution of both. If you apply the reduced phase rule, you end up with 0, which means non-variant, invariant system. So you cannot change any microscopic variable. You cannot change temperature. You cannot change the composition, and you still have the same equilibrium. So it's invariant. At point C, the system is non-variant. Temperature A and B and solution are fixed, and also the composition. Point C is the lowest melting point of the solid A and solid B, and the composition at that point it's called the eutectic composition. At this point it's called the eutectic point, and the composition at that point it's called eutectic composition. The temperature at that point it's called eutectic temperature. And we have again if you'd like to define it, you could say that the point at which 3 phases are present in equilibrium with each other, solid A with solid B and with the solution of both. And at that point, the system is more invariant. You cannot change any microscopic variable, okay, to keep that equilibrium. That's good. So the eutectic point C, the eutectic mixture, although it has a definite melting point, it's not be regarded as a compound. Even it has a definite melting point, it's not a compound. And that's because the reason for that, or the so the eutectic point C, the eutectic mixture, although it has a definite melting point, it's not a compound. It's 3 phases, solid A, solid B, and solution of both. And the reason for that, under examination of that mixture under the microscope, this reveals the existence of separate crystals. Okay, it means you have different crystals, crystal of A and crystal of pure B, in addition to the solution. So it's not a compound. Also, the second reason for that, the components are not in stoichiometric proportions. So it's not a compound. It's not a compound. Okay, great. Okay, now we're still talking about this eutectic diagram. The area above the curves AC and BC, you have a homogeneous mixture, only one phase, solution of A and B, okay? And if you apply the reduced phase rule, you end up with 2, which means you have bivariant system. So temperature and pressure can be, temperature and the composition can change it independently. To define any point at this area, both temperature and the composition must be specified. Both the temperature and the composition can be varied independently, and you still have the same phase. Very good. Okay, and at any line here we have already line AC or BC. Okay, the system is monovariant, so you cannot change temperature independently, you cannot change concentration independently. Okay, the same happens with respect to BC line. The point C, it's called a eutectic point. The system is non-variant or invariant. You cannot allow it to change. You are not allowed to change the temperature or composition. And the composition here, it's called eutectic composition. Okay, the system, we mentioned that above it's bivariant. Let us keep going. Okay, our today's task, our task today is just to determine the heat of fusion of pure A and pure B. And for ideal solution, there is a relationship between the enthalpy of fusion and the mole fraction. Okay, you can get, I mean, the origin of this equation, it's chemical potential for solid and liquid. You are not, you need not to know the origin of this one. Okay, there is a relationship between the mole fraction and the heat of fusion. You can determine it. Okay, according from this equation, just rearrange it. Okay, rearrange this equation, you end up with ln xa equal a constant. This is the boiling temperature of pure A. Okay, and okay, that's good. And this is the heat of fusion. And if you plot a relationship between ln xa and 1 over T, 1 over Kelvin temperature, you have a linear relationship with a negative slope, which is given by that one delta H of fusion divided by R, where R is R is the ideal gas constant, and this will be the intercept. So if you got the slope, okay, you have, if you multiply it with R, you end up with the heat of fusion of pure A and pure B. Okay, this is with respect to pure component B. And keep in mind that the summation of mole fractions of all components you have in a mixture should equal 1. And the mole fraction of substance A equals the number of mole of that substance divided by the total number of mole of the mixture. So it will be Na divided by N total. Number of mole fraction of B, number of moles of B, Nb divided by N total. Okay, here Xa and Xb are the mole fractions of your components respectively. Delta H of fusion with respect to A and respect to B are the heat of fusion of component of pure A and pure B respectively. Ta and Tb are the melting points of pure component. So from the curve you can get the heat of fusion, and also you can get the boiling point of pure substances, which will be our tasks for today. So the experimental part to construct a solid liquid temperature composition, Tx, where T temperature, X the composition, phase diagram for naphthalene and biphenyl. Okay, our two component, naphthalene and biphenyl system, using thermal analysis to estimate the heats of fusion of both components. You are going to use large test tubes, temperature sensor, 300 milliliter beaker, hot plate, and steering bar. And also you are going to need a water bath. Okay. Also the chemicals will be naphthalene and biphenyl. And just reminding you have to wear all safety equipments, goggles and gloves and lab coat and everything, okay, in order to the safety. The procedure, I would suggest to read it very carefully from the manual. Okay, just place the test tube into the hot water bath until it completely melted. Okay, remove the tube from the water bath and fix it in the holder on the bench top. Turn on the magnetic stirrer to ensure that the sample is continually steering. Start data acquisition to collect data temperature against time using Logger Pro device. This will provide a real-time plot of the changing temperature with respect to time. Continue until you observe a distinct arrest or thermal arrest, or break in the pattern. I will show you in the next slides. Then you may terminate the data acquisition. Oh, that's enough. Okay, just you need the thermal break temperature, which it will be the melting point of the solutions you have. To the test tube containing naphthalene, add first sample of biphenyl and start a new run and so on. This curve, okay, it's a phase transformation, or it's a temperature time or cooling curve. You could say that cooling curve. Okay, and here you starting with a pouring temperature, liquid temperature, so to say, and just to cool it, you will have something like that. It's a cooling. This is a cooling rate. You can got the cooling rate. You just measure the change in temperature with respect to time. It's a cooling rate. Okay. and you have a liquid, okay, the temperature decreasing and then becomes constant and then decreases again, okay? At that point, it's the first point at which the first crystal is solidified, and at that one, the last crystal is solidified. This is called thermal arrest or phase transformation, thermal arrest or thermal break. This is our temperature we are going to determine for today. Just extrapolating, you can get the temperature or the melting temperature or freezing temperature of the solution. Okay, that's good. Actually, you will see today something like that. Okay, the first mixture, the cooling, this is a cooling rate and temperature decreases, and you have a thermal arrest or thermal break or phase transformation. Okay, for the first mixture. Okay, this will be for the second mixture. This it will be for the third mixture. So what all you need just to determine the temperature, the melting point of each one. So just extrapolate this one to get the temperature of that mixture. Extrapolate for that one to get the melting temperature of that mixture. Extrapolate this point to get the temperature of that mixture, and just collect your data. Okay, this actually came from data acquisition or logger pro device, and you are going to plot ln the mole fraction against 1 over t later on. Okay, so the same again, you have different temperature C, and okay, and you plot the temperature against the you can calculate the mole fraction of the mixture of that one, and also for that one, and also for that one. So you have temperature against the mole fraction. Just plot it. You have a eutectic diagram or eutectic system like that one. This it will be the eutectic point, and this will be the pure boiling point of pure substance here, and here will be the boiling point of pure substance, the other one, and so on. So we're going to have these figures today, and also to create this one, and then plot 1 over t against ln x in order to calculate the heat of fusion. Okay, data analysis. You have the mole, the masses of naphthalene, and the mass, the weight of biphenyl, the mass. Okay, so you can convert them to a number of moles, and then you can calculate the mole fraction of each one. And this is this is the melting temperature of each solution. Great. Once you get that one, you can create that figure, okay, and then just plot ln x of naphthalene against 1 over t. This is temperature, melting temperature 1 over t, the first diagram for naphthalene, and then okay, ln xb with biphenyl, these 4 values with 1 over t, and just plot a diagram between ln x against 1 over t in order to get a straight line with negative slope. You can calculate the heat of fusion. This is some diagrams. Okay, this is a water pass, and this is different mixtures, and these are the temperature sensor in order to measure the melting point. Okay, will be the same. And this is logger pro device and data acquisition. It's temperature against time, and okay, this one it will be fixed by the stand here, and you have something like that one. Okay, temperature decrease, I have thermal arrest and thermal arrest and so on. See? Okay. I'm going to show the video for that. Okay, this is the water pass, and these are different mixtures between biphenyl and naphthalene, and just put them, and okay, this is temperature sensor. It's totally closed. Once it's melted, okay, you put it in the stirrer. We have a small magnet inside, and just be sure that the stirrer is working. Okay. See, and this is we fix also the large test tubes after melting the solution in it inside. Okay, and these temperature sensor which collecting to the data acquisition logger price logger device, logger pro device, and you can hear the voice of the magnet steering in order to okay, to get the right melting point of a solution. And you see here, it's collecting data or data acquisition, temperature against time. And see the temperature decreases. Okay, we can see the temperature decreases with time, and we have not reached yet the thermal arrest. Once we got it, you can get the melting point temperature. And the stirrer here is used in order to separate the temperature all over the solution you have, okay? In order to get the right crystallization or right melting point or freezing point of a solution. You will see, for example, the first one, I think it will be the red curve, or I think, or the green curve, it will be the first one. Let's see. I think you can hear the voice of the steer. And see here you read the time against temperature. We have connected the three solution together. It's no problem for the data acquisition. And it has been labeled with 1 and 2 and 3. You can know which is which very easily. No problem for that. Okay. And let's see the thermal arrest. It will show in few seconds. See the temperature is decreasing, it's cooling down, and you still have one phase, which is liquid. You have the two solvents are completely miscible with each other. And once you reach the temperature of melting of one solution, you will see the thermal arrest or thermal phase transition. Okay, see one of them starts something like that one. See this point. Okay, so you can cut the temperature correspond to this one by extrapolating, or once you put the mouse here, you can get the temperature downstairs, and that on the okay. This is the thermal arrest of the first one, or one of the mixtures, say to say. Later on, you will see the thermal arrest of both. Okay. Actually, the one you have the thermal arrest, you can remove it. But okay, we can keep it, no problem. But we know its temperature. Okay, let's see the other two. Their thermal arrest or thermal phase transformation. Let's see. Okay, this is the first one. Very good. And as I have already mentioned, you can connect more than one solutions with the Logger Pro device, which you can collect the data in order to save time, say to say. And also you can do each one individually, no problem for that. Okay, in order to save time, you can connect more than solution with the Logger Pro device. You will save some time. Okay, very good. Actually, I was planning to make it faster, but I'm wondering why it does not appear the the video toolbar, so to say. I'm wondering why. I have done it before. Okay, okay. This the first one is very clear. This temperature are needed, and we still have the red one and the other one. Just waiting few seconds, and you will see everything. Inshallah, it will be clear. You still can hear the voice of the steerer or the magnet of the magnet. Okay, and once the crystallization starts to happen, this magnet after few seconds it will be stopped because all the solution have been crystallized, say to say. Okay, we're still waiting the thermal arrest for both or for the other two mixtures. Okay. Okay. And also you can see also the temperature reading here for the red one, for the green one, for the blue one, and so on. And you can know the highest temperature it will be for the blue one. You see, it's still at this value, this one. Okay, great. We're almost there. We're almost there. We will see that. Just have a minute. You will see the thermal arrest or thermal transformation or thermal rate of the cooling curve with respect to the other two mixtures. Okay, I think it has been, the red one has been obtained, as you see, and with the green one is still. Thermal arrest for the red one you have been reached, as you see, this one. We can increase the time, so to say, in order to see everything clear. See, okay, just increase the time, and you have seen already the thermal arrest of the red one have been reached. Just extrapolate this one, this, okay. Actually, it starts to increase again due to the latent heat of fusion, but extrapolate this one, just till reach the red one and just extrapolate parallel to the x-axis, you can get the temperature. You can get the temperature, the melting temperature of that mixture or of that solution. Okay, but actually for the blue one it's very clear, just only without any increasing again you can get the temperature very easily. But here extrapolate the red one till intersects the red curve, and then extrapolate it to be parallel to x-axis or temperature to the time axis in order to get the right temperature for that one. Okay, just a few seconds you will see the thermal arrest for the other mixture, or the mixture number 3. Okay, let's see. Okay, let's see. Okay, I think it will start shortly. The thermal arrest for the green one. Picture number 2, this one. You can see the temperature of the blue one still constant. C. Temperature of red one, that one, red, and the green one is still decreasing. The thermal arrest hasn't reached yet, and of course, this kind of melting point depends on the mole fraction of both component. Okay, that's why you got different melting point of each solution depending on the mole fraction of each solution. That's very good. Okay, and you should repeat this procedure with all mixtures. We have 9 mixtures exactly, and these are 3 of them. You should apply the same procedure for the rest of the mixtures, and you end up with getting the right temperature of the melting points of that solutions, and then you can plot temperature against the composition to get the okay, we got it. We are here. Here we are. Okay, just extrapolate this one in order to get the temperature of that one. And again, just plot temperature against the mole fraction. You end up with the eutectic diagram or eutectic system, something like V letter and so on. And that's it. You should apply all the same procedure with the remaining mixture. Okay, this is the thermal arrest for the third one. Okay, this one and so on. Okay, you see it has been solidified. See, it was they were completely miscible before. Completely, it's one phase. Now here it's become solids and so on and so on. Let us. Okay, with this one, I have already reached to the end of this one, and just remembering you again, just we plot a relationship between ln x against 1 over t. You will end up with a straight line with negative slope. Just to get the slope of this one, okay. Once you get the slope, okay, just multiply it with R in order to get the heat of fusion, and also you can determine that once you get the heat of fusion, just divide it by R in order to get the boiling point of pure substances. Melting point of pure A, and you apply the same with respect to pure B. Okay, and I told you if you like to have okay, I'm going to discuss it later on the phase diagram of the water separately, and why you got negative slopes and what the benefits of that negative slopes until we meet again. Before that, I hope everything is clear with respect to binary solid liquid phase diagram, and if you need any comments, any question, just contact me. Inshallah, I will reply you immediately. And until we meet again, I wish you all the best. Wassalamu alaikum wa rahmatullahi wa barakatuh.